Welcome everyone to the afternoon session. So we'll kick off with Zhiwei Yun, who will tell us about an irregular Deligne-Simpson problem and Cherednik.
I'd like to thank the organizers for the invitation. So this talk I will relate the main themes of this workshop, representations, to something that's a little bit outside of the main topics. The Deligne-Simpson problem. And hopefully by the end of the talk, this connection will be demystified. Okay, so this is joint work with Konstantin Jacob. So let me first talk briefly about what the Deligne-Simpson problem is. So in general, it is some existence question for connections on algebraic curves. Okay, so this algebraic connections, possibly with the poles, meromorphic connections on the algebraic curve. So more precisely, we can fix some local data at finitely many points. For example, here I can ask it to be regular singularity, to have regular singularity with prescribed residue. So the means the connection will locally look like some matrix. Okay, some expansion like this times dt over t. Okay, so t is the local parameter at this point of your Riemann surface, and this connection form has only a first order pole. So that's regular singularity case. And you may ask this A0 to be fixed, or at least its adjoint orbit to be fixed. And you can fix such an adjoint orbit at each of these finitely many points and ask if there exists a global algebraic connection which has the prescribed residue at all these points. So this is formulated in terms of connections. You can also, via Riemann-Hilbert, you can reformulate it using product of matrices, which is more concrete. So basically, you're asking whether you can find three matrices, and if your puncture, sorry, so yeah, I drew a surface that's too complicated. I didn't have, I was in the genus 0 case. It would translate to solving a matrix equation. Three matrices product equal to identity, and each of them lies in a prescribed conjugacy class. So you're asking whether solution exists. It's a very concrete algebra problem. So this is a more classical version of the Deligne-Simpson problem. It concerns connections with irregular singularities. So what we will consider is an irregular version of the Deligne-Simpson problem. So let me briefly recall some facts about irregular singularities. So if the connection form has order higher than the simple pole, we call it an irregular connection. And what I'm going to review is a normal form for any connection. Roughly speaking, all the irregular terms can be simultaneously diagonalized up to extracting a root of t. Okay, so so we have this disk, this puncture disk. Think of this with parameter t. Introducing a root of t means we pass to a cyclic cover. This parameter is called a t1/m. If I have a connection here, I can pull it back to this cyclic covering. And the normal form says, after such a pullback for an appropriate m, then any connection can be up to formal gauge transformation. So this is a formal gauge transformation. You can arrive at a form that looks like A minus T over M. Plus 1/L. Plus higher terms, higher meaning regular terms. And the point is, all these A negative terms are lying in some carton are diagonal matrices. So this is just follows from the classical theorem of Levelt and Printing, the normal form up to formal gauge.
Sorry, is that not an assumption that they are diagonal? I mean, you're assuming that the leading order term is diagonalizable?
So the point is, you can always formal gauge it to a diagonal matrix, and not just the leading term, but all the irregular terms simultaneously. But of course, the residue part, you can't do much to it.
Yeah.
Yeah, but the worst terms are actually simultaneously diagonalized. So this has a version for any G. Let's now work with the generality G. Say algebraic group. So let's work with the G connections. And there's a version of this normal form theorem. So normal form also holds for connections over, or G connections over a puncture disk. Says up to some cyclic pullback, you can formally gauge transform. Now the gauge transformation is using an element in the loop group of G with this parameter that's T, the root of T. Gauge it to something similar. Where all the negative terms lie in a fixed carton. Oh, the algebra of G. So let's make a definition here. So we say we call such a connection over a puncture disk isoclinic of slope E over M. If the leading term here is regular semi-simple. Okay. Yeah, so for type A, it just means the leading term has distinct eigenvalues. And so this word comes from the notion of slope of an irregular connection, highest order pole that appears in this expansion. And this means equal slope. So now I can formulate the precise version of the Deligne-Simpson problem that we are solving.
Are you claiming that somehow it's independent of the choice, right?
Yes, yeah, that's a good point. So this number is intrinsic on the original connection. It doesn't depend on which cyclic covering you are pulling back.
And also this matrix.
Yeah, also the gauge transfer. This matrix. This is so up to, well, yeah, the conjugacy class is well defined.
Does it correspond to the Stokes data forming a torus?
Yeah. Yes, exactly. Yeah. In type A, yeah. Okay, so the precise formulation of Deligne-Simpson problem. So I want to denote it by this slope, which is D over M, and another piece of data is an adjoint orbit in the algebra. It doesn't have to be nilpotent. It's any orbit under the adjoint action. So this is the question asking whether there exists a G connection, nabla on P1 that's meromorphic. It has poles at 2 points, but at 0. So near the puncture disk at 0, this has a regular singularity with residue in O. The prescribed adjoint orbit. And second, near infinity, this is isoclinic slope. This is about P1 with 2 punctures with regular singularity at 0 and irregular singularity at infinity. So the meaning of this isoclinic, it just means you expand it in this normal form up to some cyclic covering, and the first leading the highest order pole is this rational number that you're given in the beginning. You can refine the problem to fix also these polar terms. So you can refine this and ask for a similar existence problem, not just fixing the slope, but also fixing all these terms. I'll just denote it by A negative. So you fix all these coefficients in Croton and ask for the existence. Turns out this has the same answer as this coarser problem. That means if you have a connection for one such A that has a regular semi-simple leading term, then it has a solution for all such A. So let's just simplify the notation and consider such a existence problem depending only on these two discrete parameters, a rational number, a positive rational number, and an adjoint orbit. Okay, so our task is to just to tell from these two pieces of data, yes or no. That's a very well-defined question. So now I'm going to formulate the answer. I'll formulate two versions of solutions. First, the algebraic solution. So from the given data, I'm going to first introduce an operation that turns an arbitrary adjoint orbit into a nilpotent orbit. So this is a kind of very simple procedure. Basically, you want to scale your adjoint orbit by t, and as t goes to 0, you take the limit. Okay, so this is defined, characterized by following. So scale your adjoint orbit by some t, and maybe let's call this e, not to be confused with that parameter. Sorry, so let me just maybe so let Gm, this is the dilation of elements in the Lie algebra, act on O. You take the saturation and take closure. So this is going to hit the nilpotent cone. If you intersect with the nilpotent cone, this will be an irreducible G invariant variety, and therefore it has to be the closure of some orbit, and that's the definition of O nil. So, an example.
Yeah, it's irreducible.
I think it's yes. So let me see why is. Yeah, you can see this by reducing to the levy, just to kind of look at where this separate the semi-simple part and the nilpotent part. You can rewrite this using some parabolic induction diagram, and from there you can identify this procedure with Lustig-Spaltenstein induction. So maybe there's a direct way of arguing this is irreducible, but at least from that way, you can see closure of a single orbit with the same dimension as O. So if you start with the regular semi-simple, or in fact, any regular adjoint orbit, then because of the dimension has to match, this also has to be the regular nilpotent orbit. Yeah, so if you start with, let's see, in type A, you start with
Then it's wrong recipe, right?
sorry?
It's the wrong recipe. Ah, no, sorry, no.
Regular, yeah, so for example, regular semi-simple, regular nilpotent. Yeah, at the other extreme is you take something semi-simple, but not necessarily regular. So yeah, so if O is O of something one n, and these eigenvalues are repeated according to some partition lambda, then nil. So so if this lambda is the trivial partitioning to singletons, we already see from here this has to be a single Jordan block. So here, yeah, so this is the Jordan type is the conjugate coefficient. Okay, so that's some notation I need to formulate algebraic solution. Now, write down a theorem. Maybe one more piece of notation. So the answer will be formulated using rational Cherednik algebra. Of type, the same type as G. So well, it's only cares about the wild group. And this has a simple module. It's called L triv. So this nu is the same nu that is supposed to be the slope of our connection, and this is a unique simple quotient of the Verma module with parameter nu. Okay. So then the what I really care about is only the W action on this guy. In particular, this is a finite wild group acts on this vector space. And the theorem says given nu and O, so add an orbit. So this theorem to formulate in the nicest form, I assume this M is so-called elliptic. I'll explain what this means. Then Deligne-Simpson for the slope and this described adjoint orbit has affirmative answer. Namely, there exists such a connection if and only if, as a wild group module, L nu triv contains the Springer representation attached to this nilpotent orbit. This is the Springer representation of W attached to the nilpotent orbit O nil and the trivial local system. So that's the first theorem.
Could you explain what the E nil is?
Yeah. So
Springer. Okay.
So I've used both pieces of data. So nu appears here. This O it only appears through its limit in the nilpotent orbit. So let me explain what elliptic means. It's not an essential restriction. So it turns out that if nabla is isoclinic of slope E over M in reduced form, I mean, lowest terms, then this m, this denominator cannot be arbitrary. And m is a so-called regular number. This means this refers to a notion of regular elements in the Weil group defined by Springer. An element in the Weil group is called regular, namely if it has eigen vector that's regular. So there's a reflection representation of W on the carton has an eigenvector inside the regular semi-simple locus away from the walls.
So trivial one is.
Trivial is an example. And another extreme is the Coxeter, any Coxeter element. So examples, and okay, let me finish the definition of regular number. So a regular number is the order of a regular element. So examples if W is Sn, then W so regular numbers are either divisors of n or divisors of n minus 1. So in the first case, they are orders of cyclic permutation to some power. And in the second case, you just take a slightly shorter cycle. In both cases, they give regular elements. You can check. That's it. So these are the list of regular numbers in type A. In other types, I mean, classical types is somewhat similar. And exceptional types, Springer listed all regular conjugacy classes and regular numbers. For example, in E8, there are 12 regular. So it always ranges from the trivial element is a regular element, the order 1, up to the Coxeter number is 30. There are 12 nice numbers in from 1 to 30.
How do you determine it's here?
Oh, there's a criterion in terms of exponents of the group. Degrees of invariant polynomials for the reflection representation. And these okay, M is called elliptic if this M is the order of an elliptic regular element. So elliptic meaning there's no eigenvalue 1. So type A, we only have a single case. Elliptic regular. So these notions appear in the work of Ragnolo and Vassero in their classification of finite dimensional spherical representations of Daha. those parameters that allow finite dimensional spherical representations of Daha are precisely this d over n, where n is regular, elliptic regular. And the appearance of this elliptic regular condition is not a coincidence, and this result is actually closely related to what we are doing here. Okay, so I have stated this theorem completely. So next I will state a geometric version. Geometric solution to the Deligne-Simpson problem. So it uses the notion of affine Springer fibers attached to homogeneous elements. Psi in the loop group with the algebra of slope, same slope. Okay, so the homogeneous elements also first appeared in Aragnol and Vasseuil's work as part of their geometric construction of representations of Daha. So roughly speaking, homogeneous elements are those such that the loop rotation. So you can think of this as a Taylor-Laurent series with coefficients in the Lie algebra, and now you can do loop rotation to your parameter t. And let's see. So if you do it with weight m, then on the other hand, you scale your element by s to the d. This is just the scaling the Lie algebra element. If they turned out to be in the same adjoint orbit, so have the same image in the adjoint quotient, then this psi is called homogeneous. So I mean, in Roman's talk, there's the simplest kind of homogeneous element of slope 1 appears. Namely, you just take t times some x, where x is irregular semi-simple in G, constant vector, and then just put in degree 1. So this is homogeneous of slope 1. And so in type A, it's easy to write down examples of any possible slope. For example, smallest possible slope. You and just allow more general. So subdiagonal ones, and then you put this t to the d in the corner. E is prime to n. This is homogeneous of slope e over n. Okay, so now the geometric solution. So x psi, this is the affine Grassmannian version of the affine Springer fiber. G in loop group for other groups such that adjoint action of G inverse takes psi to G of all power series. And this variety has a evaluation map at t equals 0. So you can, if you have such a G, you can look at this element and just evaluate at t equals 0. You get some element in G, but we're only well-defined up to adjoint action of G. So there's a well-defined map to this quotient. In fact, if you start with psi that's topologically nilpotent, then this map will always land in nilpotent cone. And for any nilpotent orbit, I can define x psi potent to be the preimage of this given nilpotent orbit. And similarly, I can put a bar. So theorem. So let psi be homogeneous, any homogeneous element in the loop Lie algebra of slope mu. Then the Deligne-Simpson problem for mu and arbitrary adjoint orbit O has an affirmative solution. If and only if you look at this variety, this subvariety of the affine Springer fiber, using this nilpotent induced from this given adjoint orbit, this subvariety is not empty. So that's a geometric criterion for the Simpson problem. The case. Yeah. Okay. So yeah. Now the third kind of solution is given completely down to earth list of nus and O's, right, using these two theoretical solutions. So that's me give you some very explicit answers. So yeah, these we can view as tools to make concrete calculations. So we succeeded in giving completely explicit answers in all classical types so classical types for any slope, any O. And for all types, but then the denominator of the slope is restricted to the Cox-Sternal. O. So and there, I mean, this algebraic solution actually gives you an algorithm to calculate the answer. So this experts in Daha know how to figure out the character of this L-nu triv as a Weil group representation. So in principle, you can use a computer to compute the inner product using character table. We did it. We did it for F4. Just to illustrate that this is an effective way of computing things. So let me
with the computer.
yeah,
For
F4,
the computer.
probably no. F4 we did not use computers, but we use some existing tables, which may already dependent on computer. Okay, so let me give some extreme cases just directly followed from these theorems.
We can short questions. Whether for every slope there is a homogeneous element of this slope?
Yes.
Can I ask that?
Yeah.
So in both of these statements, the right-hand side says something is non-zero.
Yeah.
Can you refine the left-hand side? Like there's a lot of ways to not be zero. Can you refine the left side to make it?
Yeah, very good question. So we can say, we can ask about the moduli space of such connections and, for example, calculate a dimension. Such moduli spaces. You can read off that dimension from the either the algebraic answer or geometric answer here. So the dimension will be is something like twice of this guy. But it's, yeah, so there's a more refined state. Okay, so easy cases. If the slope is at least 1, then this Deligne-Simpson problem is always okay for any adjoint orbit. Another case, another extreme is mu is 1 over the Coxeter number. This is the smallest possible slope you can get for any irregular connection. Then O has to be a regular orbit. In this case, 1 over H, O with affirmative, if and only if O is a regular orbit, regular adjoint orbit, and like its limit is an irregular nilpotent. And another case we can say uniformly, slightly below 1. So then, so we should roughly expect when the slope is large, then we are allowing more and more orbits O. When the slope is small, we are allowing fewer orbits. So this should be pretty close to allowing all orbits. Indeed, all you need to throw away is the 0 orbits. Yeah, so one. So this has affirmative answer. If and only if O is not the 0. Namely, your connection needs to have a singularity at 0, but that's the only restriction. So let me give a complete answer in type A. So I should mention that when slope is d over n, so this is the type A elliptic case. This is already solved by Daniel Sage and his co-authors, Okani, say from last year. They give they actually write down connections. So it's more explicit than the answer we give. But we are dealing with more general groups and more general slopes. So in type A, we said there are 2 cases. Either your slope is d over m, where m is the divisor of n. So in this case, condition is simply this O nil is bigger than or equal to the orbit that has equal parts with E parts, equal parts. Okay, so let me call this lambda, so partition ND. What is ND? So is the most balanced, namely all the parts are almost equal partition with D parts. As long as your orbit is bigger than this, you're okay. And you can go one more step to spell out what it means for the limit nilpotent orbit to be bigger than this in terms of Jordan types here. You can make it more explicit. Another case is when M is a divisor of M minus 1, then the condition is that O nil is greater than or equal to similar thing, but then your partition, the most balanced partition B parts of N minus 1 together with the trivial part. And you can, I'm not going to copy all the answers here. You can see from the paper all the classical types are computed. And the answer always involves these most balanced partitions.
There is always the minimal one, as answer is always a greater or equal than something.
Yeah. So that's another feature. So there's always a unique minimal nilpotent orbit, such that the Deligne-Simpson problem has an affirmative answer. Maybe I can briefly explain the proof. So here's the Deligne-Simpson problem, which is about connections. Modules. The algebraic version of the theorem relates these two, but the geometric version relates Deligne-Simpson problem to something intermediate, the affine Springer fibers. So this connection goes through affine Springer fibers. This part of the diagram is better understood. So again, by the work of Baragnola and Vassero, we construct actions of different versions of Daha on cohomology or K-theory of affine Springer. In particular, these homogeneous affine Springer fibers. And in my work with Oblonkov, we give a geometric interpretation of the rational Daha acting on some version of cohomology of Springer fibers. So these go into relating the geometric criterion with the algebraic criterion. So this part is more recent. We need some mechanism of connecting a moduli space of connections to affine Springer fibers. So this is already mentioned in Roman's talk, originated from work with Roman. I'll just write the initials, Pablo Boxeda Alvarez, Michael McBreen, self. Not quite the same moduli space, but closely related. So namely, we construct a Hodge moduli space that's a one parameter family, classifying lambda connections. So on the one hand, if you taking the fiber over 1, this gives the round moduli space, depending on the starting data is always a homogeneous element in the loop the algebra of a given slope. And the fiber over 0 is some Hitchin moduli space. So Roman mentioned we can kind of define a nice where this turns out to be symplectic and contains the affine Springer fiber, that version of affine Springer fiber as a Lagrangian, the conic Lagrangian. Everything is contracting to that Lagrangian. In our version, it's slightly different, and we want the Grassmannian version of the Springer fiber to appear rather than black version, but the difference is minor. So the idea is so we want to show this space is non-empty. I also need to put in some orbit, put an orbit like this decorated, pass to some subvarieties. Depending on the residue at 0, here it will depend on this limit nilpotent orbit. So you can imagine there's a family whose generic fiber is the moduli space of the kind of connections that the Deligne-Simpson problem is looking for. And the special fiber is some Hitchin moduli space that contracts to Springer fiber. So with enough smoothness of this space, we can say there is a point that this fiber is non-empty if and only if the limit is non-empty. So you need some smoothness of this moduli space for that to be true. But yeah, it is true in this situation. So this is how you can reformulate the Deligne-Simpson problem into something that only depends on the affine Springer fiber by this limit procedure.
And these spaces only exist for homogeneous elements?
Yeah, so it has these nice properties only when psi is a homogeneous element.
But still you can make a definition for any guy.
No, that will depend on some choice, like globalization of your element. So this psi started life being an element in the living on the formal disk around 0. In the case of a homogeneous element, there is basically a canonical way of globalizing it into a monomial int. It's not homogeneous, you have to make a choice how to globalize it to some meromorphic basically view it as a rational function, g bracket t, to globalize it. And that's not a canonical choice. And the corresponding moduli space I'm not completely sure, but I don't have a way to make it symplectic. Okay, so that's the idea of the proof. So consider these moduli spaces. I want to advertise. Yeah, so maybe just to say how we get these explicit solutions in classical types. We use the geometric criterion directly, not using Daha. Explicit solutions in classical types. Namely, from here, we know we need to calculate these affine Springer fibers with a particular whose reduction modulo T lies in a particular subset of the nilpotent cone. So there's a subvariety of the affine Springer fiber. And there's a way to calculate these varieties. Can be calculated, or at least to tell whether this is empty or not, by something I call skeleton. This was introduced in my other paper for a different purpose. So what is skeleton? I think it's a basic object, but with geometry I don't fully understand. So let's recall we have how affine Springer fibers are defined. We have affine Grassmannian, and we look at the infinitesimal action of some Lie algebra element and take fixed points. So that's next slide. Now, what if I take, instead of a single element, I take the whole Cartan subalgebra containing it. So basically, I take the whole centralizer of this guy, which will be taken inside the loop group. Okay. So this will be a maximal torus in the loop group, which may or may not split. At one extreme, it's some kind of a pro-algebraic group. If the splitting type of psi is elliptic, at the other extreme, it may just be torus double bracket. And let's always take the neutral component of this guy. So this is the loop group of some possibly non-split torus. And then look at the fixed points of this whole thing. So let's call it XW. W denotes the splitting type. Of this torus is classified by a conjugacy class in Weil group. So the isomorphism class of this subvariety of Grassmannian only depends on the splitting type. So this is some finite dimensional subvariety inside the affine Grassmannian. The question is, what do they look like? So I was able to make explicit calculations in classical types. In half of the cases, namely type A and C, they're just points. In the other half, namely orthogonal groups, they can be positive dimensional, but very explicit. I think it would be interesting to understand them for all groups. For exceptional groups, I don't have a way to calculate these varieties. So if we could understand these varieties better in exceptional types, then we can extract from those descriptions explicit answers to the Deligne-Simpson problem, also for exceptionals. Stop here.